Onward with fluids. I want to propose to you a tube filled with some fluid, and this is going to be a little bit counterintuitive, but the idea here is I've got this tube and it's open at both ends, and I've put some liquid into it, and the liquid's at this level over here and this level over here. Immediately you'll think, wow, that's not going to work. You know that pressure depends on depth. So you would say that right here the pressure is low, and you'd say right here the pressure is high.
What about guys that play saxophone in front of Busch Stadium?
This pressure is high, this pressure is low, because the pressure differential, I guess there's a pressure that's happening because of this height. So this is height 2, and this is height 1. And you believe that they will equilibrate. If it's in a gravitational field, then they're going to go to the same level. And the reason that water seeks its own level, which is sort of a phrase that you hear people say, water seeks its own level because it's minimizing gravitational potential energy. If you've got a low pressure here and a high pressure here, then the high pressure is exerting more of a force to the left than the low pressure is exerting to the right. So there's a net force to the left, and then the water accelerates to the left. Now, of course, you believe it'll probably also slosh. It'll go shoop, 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 shoop for a while until gradually friction causes everything to calm down, and we get this new water level, which is hopefully right about here. Doot, 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 and doot, 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 doot. That will be the new water level, H nu, where H nu is going to be the same for these two sides. Cool. But what if it were slightly more complicated? What if we put two fluids into a similar shaped tube of glass? In this problem, I'm going to put, let's assume I'm making this all the same cross section, so it's nothing weird. I'm going to put a really thick fluid over here, and it on top of it, on one side, I put a really light, bubbly fluid, something with much less density over here. So here's this bubbly, light, pleasant fluid, and underneath it is this thick, muddy, gooey fluid. Their densities are different, and notice that I'm going to assume that this has come to equilibrium. Notice that the height is not equal. You've got, well, here's what I want you to notice. I guess I'm arguing that the height, the pressure here, pressure left, is the same as the pressure at the right. Would you agree that these two are equal if it's in equilibrium? Of course so, because the cross-sectional area is the same, the pressure is going to be the same, and this pressure over here is pushing to the left, that pressure there is pushing to the right, and they don't have any accelerations because all the forces are canceling out, and everything is nice and steady. But this height here is very important. I'm going to call this the 0 level, right here. This is h equals 0. So this I can define as h1, and this I can define as h2. These two heights are different because if we say pressure at the bottom, remember pressure at the bottom is pressure at the top plus rho g h. These heights are different because, baby g is not different, but because density is different. This is density, and these pressure, let me emphasize that this is a straight line, this is a straight line, and that's a curve. This is the density of the fluid. So we can say that, oh man, we know the pressure at the top is the same, right? And we know the pressure at the bottom is the same. And therefore, we know that we can relate these two heights because I guess we can say rho 1 times g times h1 equals rho 2 times g times h2. If we wanted to find the density, let's say we know the density of this dense thing. If we wanted to know the density of the thing that is light, fluffy, and airy, we'd say density 2 is density 1 times g times h1 divided by, well, I guess I'm going to get g times h2 right there. And these suckers, well, these suckers are going to cancel out, and it's simply, well, it's simply the density of the first fluid times h1 over h2. This seems to imply, oh, sorry, I need another equal sign there. This seems to imply that the density of fluid 2, that's this guy over here, and the density of fluid 1 are different, and fluid 2 is less dense than fluid 1 because H1 is small and H2 is big. And that confirms our realization that the energies are the same. Now let's consider another way of looking at this. This chunk of mass right here must be exactly equal to this chunk of mass right here. This chunk of mass is equal to that chunk of mass. So if you found the volume here and multiplied it by the density, then you could say this volume multiplied by its density is also the same. It's very reasonable. The volume here is going to be the area times the height 1, and we need to multiply that by the density, which is rho 1. That's going to be equal to the area times height 2, that's the volume over here, times rho 2. And this simplifies to exactly the same relationship as we had previously. So you see it's valid to see it in a lot of different ways. Essentially what we're doing is we're minimizing gravitational potential energy. This is why if you put one fluid on top of another fluid, it will not necessarily reach the same height. Water seeks its own level, but not when you've got two fluids mushed together. I want to ask you a whole bunch more questions, but I think I'll just conclude with Pascal's principle. Pascal noticed that if you increase the pressure at the top, if we increase pressure at top of fluid, we increase pressure everywhere. And in fact, we increase pressure everywhere by the same amount. So let me point out then that this is sort of like any disturbance in a fluid is transmitted through the rest of the fluid. And this is sort of an equilibrium kind of thing. Gradually this happens. It has to do with the speed of a wave moving through the fluid. So it's not an instantaneous thing, but it happens rather quickly. If I squeeze one part of a bike tire, that pressure is going to change everywhere else on the bike tire. It is what it is. Let's end with one more definition. This is called gauge pressure. And gauge pressure is very important. It's the actual pressure minus the atmospheric pressure. And so if, for instance, I give you a bicycle and I say this bicycle, if I pump up the tires on this bicycle right here, then let's see, I've got a bike pump. It's called a floor pump, and it's got a gauge on the front of it. And if I hook this up while the tire is flat to my bike tire, then it reads pressure equals 0 when flat. But you know that the pressure of the air inside there is the same as the atmospheric pressure. So in fact, what we're doing is we're measuring gauge pressure with the gauge of a tire pump. That's the whole point. Gauge pressure is measured with gauges in atmospheric pressure. So we subtract the atmospheric pressure and we say the tire is flat when it is the same pressure as the atmospheric pressure. Now the reason that a tire, when it's pumped up, can resist the bike falling down to the ground, the reason the tire has some oomph, some force it can exert on the outside world, is because there's a pressure difference. And that pressure difference is what causes a force that the tire can exert on the outside world. Goodbye.